Alright guys, so we're going to start the review for Unit 2. I'm going to go over some questions here that I isolated depending on your questions that you guys asked, and something that I kind of wanted to read, and some things I wanted to review because maybe we didn't talk about them, or I just want to make sure you guys understood. So for number 6, it asks which has the highest melting point. These are all metals: lead, gold, osmium, tungsten, mercury. They're all metals, and they're all in this 6th period. We have tungsten, we have osmium, we have gold, we have mercury, and then we have lead. So usually the transition metals are going to have the higher atomic or melting points, because they can form, because of their S and their their d orbital electrons, they can form some pretty complex structures. So like when they bond, so like when gold bonds to itself, it has those d and s electrons, so it can form like really complex crystals or shape atomic structures. So that's kind of like what we see. So the reason gold is it increases from the left to the right across the transition metals, except for this last group. And this last group's a little bit weird because they have the full electron in their D shell. So then it kind of changes. So these will go back down. So copper, silver, gold will have higher melting points than zinc, cadmium, or mercury. And in fact, mercury is a liquid, so we know for sure it's not that one. This is a liquid at room temperature, so we know it has a lower melting point. So now lead follows this trend. Tellurium is going to be a little bit higher than mercury. Lead's going to be a little bit higher, but it's not as high as these here. So because these are our transition metals, and again we increase as we go across, gold is going to have the highest melting point. And remember, for melting point, what dictates melting and boiling point, those that have, so atoms and compounds but it can kind of it's a little weird. So some of them, you know, it doesn't really follow a pattern. It's more by like the, what's it called, the group itself, or the column. So number 7 said, which of the following is an isotope of an element with 20 protons and 20 neutrons? Remember, the protons, they determine the element. So if you look for number 20, that's calcium. So here we have, that would be the correct answer. This one I wanted to talk about. We haven't talked about what isoelectronic means, but isoelectronic just means the same number of electrons. So iso means same, and then electrons, so same electron. All of these are going to have 10 electrons, so every single one of these has 10, but they don't have the same number of protons. So magnesium has 12 protons, sodium has 11, and then 10, and then 9, and then 8. So it wants to know the smallest radius. Remember, according to Coulombic force, the higher, so we have here CF is equal to K, this is a constant, Q1, Q2, and then the radius square. So we're trying to figure out the radius here. We know that if we increase one of these, we're going to increase this, and that's going to decrease our radius. Okay, so we have a lot more protons here attracting those same 10 electrons, so it's going to bring those electrons closer together. That's why magnesium has the smallest radius, because those 12 protons really attract those 10 electrons. Okay. Okay, then we have number 9. You guys talked about ionization energies. Ionization energy is basically how much energy does it take to remove one electron. That's it. And you can remove the first electron, then the second, and then the third. And this chart tells us the ionization energies for an element, and it's removing 5 electrons. That element is one of the period 3 elements. So it's going to be in this row right here. So it's one of these. Now, if you look at it, the first one is 577, and then it kind of almost triples, right? And then it kind of doubles here, and then here we go from like 2,800 about to 11,000. So there's a very, very, very pronounced jump here. What this tells us is this is probably really doesn't want to lose those electrons. It's like, no, I'm perfect. So that's telling me that it's finally at the noble gas configuration, because your noble gases, they're going to be really high ionization energies because they do not want to lose electrons. So what that tells me is it took 3 electrons before I got to my noble gas. So if it's one of these, it would be aluminum. And the reason it's aluminum is because it takes 3 electrons before it can be neon. And that's why I know it is aluminum, okay? So remember, there's a lot of you guys, or a couple of you asked about ionization energies. It's just how much energy does it take to remove an electron? And we see these trends here. So remember that as you move from left to right on the periodic table, especially if you're in the same group, or the same period, row, you're going to see an increase as you move from left to right. And the reason is we're adding more protons to the same energy level, and those electrons are getting more and more attractive. We're not adding any space between those protons and electrons, so that's why we see an increase in ionization energy. But when we go down a group, we see a decrease, but as we go up, same thing. We have less space between those electrons, but adding more positive protons, so that's why. Alright, this one says which of the following has the largest atomic radii? So if you look at our trends, atomic radii or radius goes down. As you go down a group, it will increase because we're adding more energy shells. And then as you go from right to left, it increases. So something down here is going to have a much larger atomic radii than if we were to do helium. We'd have something very small. Okay, so in this case, if we look here, it would be, we have hydrogen here. We can go back to, or let me bring the periodic table over here. We have hydrogen here. We have manganese here. We have chlorine over here. We have rubidium over here. And then we have silver right here. So right away we're going to look towards this corner, and we see that rubidium is the lowest, and it's also the most to the left. So rubidium would have the highest atomic radii. Which of the following has the greatest ionization energy? Again, our ionization energy increases as we go from left to right and as we move up a column. So in this case, these are all, let me erase this really quick so we know what we're talking about. Potassium, calcium, so we're all in period 4. Potassium and calcium, iron is right here, gallium and bromine. So if we're in the same period or row, it's going to increase as we go across. So bromine would have the greatest ionization energy. Oh, sorry about that. Okay, I wanted to go over here because somebody had questions about resonance and polarity. So it says, actually I wonder if I'm going to cover the resonance. So if you can kind of ignore this resonance for now. I'm going to cover it in a little bit. Let me just... I'll cover it right now. So it says, which of the following bonds is most polar? So remember, polarity, it happens when you have an unequal sharing of electrons. So unequal sharing of electrons. And we can find this out using electronegativity. So the higher the difference in the electronegativity between the two, then the more polarity you're going to have. So when we're talking about bonds, that's how you would figure it out. Okay, so if we go back to our trends, we see electronegativity follows the same as ionization energy, except we're not going to have any electronegativity for the noble gases. So let me draw it down here. And do it light blue. So as we move across, except for these are not going to be on there because they have no electronegativity. And then as you move down, we're going to decrease. So electronegativity decreases. And then this is increase. So just in case you forgot what electronegativity is, it's basically how much an atom wants an electron. And the reason we have 0 values, or these are all 0, is because they don't really want electrons. They're perfectly satisfied because they have a full shell. Okay. If we look here, we have nitrogen, and then we have chlorine. That's about the furthest. So carbon and nitrogen are pretty close. They're going to be like 0.5 away in difference. Sulfur and sulfur, they're the same, so they'll have a 0 difference. Bromine and bromine, again the same, so they'll have a 0 difference. Oxygen and sulfur are right below each other. At the most, they might have a 1, but that, I think it's less than 1 actually. And then, so nitrogen and chlorine are about the furthest away, so that's why we can say they are the most polar. And the reason they're the most polar is because they have the highest difference between the electronegativity values of the two. Now, how do we know when we have polarity in a molecule? So here with the bonds, when we're just talking about 2 atoms, we can kind of look at the trends of electronegativity and figure that out. Here, it says which of the following is most polar molecule. You look at the structure and you see, is there any differences in the shape, kind of. So if we have chlorine and chlorine, they're the same. We have the same number of electrons on both sides. So that's not going to be polar because the electrons are evenly distributed. Okay? Here we have a carbon dioxide, same thing. We have our electrons evenly distributed. The oxygens balance each other. So that's not going to be polar as well. With this chlorine, we have carbon in the middle. There's no electrons on the carbon. And then the chlorine each have electrons, but they're again evenly distributed all around the central atom. So no polarity there. Now, with this, we do not have an even distribution of these electrons. The reason is, if I were to draw this out, we have nitrogen, and then it has 2 electrons here, so this is a lone pair. Then we have fluorine, and each fluorine has 6 valence electrons on it, or 3 lone pairs, however you want it. So you can see so each of these has its own little bubble, right? And then depending on that, it'll form a different shape. So we have a lot of electrons here, and then we just have 1 electron pair there. So you can see there's not necessarily an even distribution. And even if I were to draw it like this, so I'm spread apart as far as possible, I'm still not going to have an even distribution of my electrons all around. I'm still going to have this versus you see I have more electrons down here than I have on this nitrogen. So that's why we have some polarity here. And that's how you would know. So another example of one of the most polar compounds that we have is going to be water. Let me just get these out of the way. So when we draw water, the reason it is very polar is we have oxygen in the middle, and then we have 1, 2, 3, 4, and then 2 hydrogens. So you can see here, we do not have an even distribution of the electrons. Over here we have almost no electrons because this oxygen is very electronegative, so it's going to be pulling these, and these electrons are on this side, so we're very electron negative or heavy on the oxygen, not so much on the hydrogen. And that's how you know you have a polar molecule. Okay. We also had questions about the energy diagram and bond length. So this one, it specifically gives you this graph, and then it shows you the distances in nanometers and then the energy in joules. So remember, at the lowest point, that is when we are basically at the stable structure. This is as far as they should be. And this is the energy associated with that bond. So this one kind of tricks you. So it says, what is the, and I know when I first saw this, I was like, oh, it's, according to the graph, it's, you know, -335. But it's tricking you because it talks about the 2 isolated atoms. So remember, we're talking about distance here. And if we have 2 atoms, the bond length, sorry, I know this looks a little strange. The bond length is the difference between the 2 nuclei. So here we have a nuclei, here we have a nucleus, and that's the distance. We get to a perfect spot here, which is like 0.15. But the further, if I were to separate them, and I would make it go more and more and more this way, then it would get to a point where they would be isolated. They wouldn't be next to each other. So we'd have something along the lines of this. They're so far that the Coulombic force, or the attractive forces between these 2 atoms, protons and electrons, would no longer be there. And we get very, very close to 0. So when it says what's the energy of 2 isolated atoms, basically saying 2 atoms that have nothing to do with each other, it's going to be about 0 joules. So if they have nothing to do, there's no attractive forces, no energy between those 2. For number 18, it says, what is the bond length of the bond between the 2 atoms? So if you see here, this is our stable bond right here. And if we just go up to the length, and you can see it's probably 0.14. These don't make sense because it's not less than 1, or 0.1. It's not greater than 2 nanometers. 2 nanometers is not even here. 0.3 would be all the way over here, and it's not that. 0.4 over here. So B would be the correct answer. Then we go to the last one. Says, what is the bond energy? So the bond energy would be here at that point. And you can see it's not 0 because then they wouldn't be associated, but they're bonded there. It's not -110 because we'd be here. They're too close to each other. It's not -10, be right there. It's not -422 because it doesn't even reach that. So it would be -330, and that's how you would read it. Okay, so just to review these types of bonding diagrams or potential energy diagrams between two atoms, whatever you want to call it. This is the internuclear repulsion forces. So remember, the closer they get, those protons and electrons are repelling each other. So that we get to this point down here, that's like the stable where it's just enough distance where they're attractive, but they're not repelling anymore. And then if we move further and further away, so now the energy decreases because we're getting too far. So there's almost no energy. There's no attractive forces there. So at this point, that would be the potential energy for that bond, or the bond energy. And then here, depending on where that point, if you go to the x-axis, that would be the bond length. Okay? And remember, if you have a double bond or a triple bond, that's very much going to increase or make this peak go a lot lower. And it kind of changes. So this would be a single. We can say this is a single, this is a double, this is a triple bond. Okay, so here I have now our structure. Some of you guys still had questions about how to draw these Lewis structures, and I'll kind of go over that in number 21 when we talk about resonance. You guys also had asked about formal charge and what's the difference between formal and resonance. So formal charge is just a formula that you use to calculate the charge on an electron when it's drawn out in a Lewis structure. If we were to take this right here, the reason I say none of these are correct is because they forgot to put some electrons there. So we look here, and the first thing we want to do whenever you have it, just make sure you calculate the number of valence electrons. So sulfur has 6, oxygen has 6, chlorine has 7, but there's 2, so we have 14. So that equals 26. Okay? So yeah, that's what you want to do there. Now, one of the easiest way I find to do this is to, when you draw your Lewis structure, is to actually just draw each electron or each atom and put it with its valence electrons around. So we know sulfur is going to be in the middle because it's the least electronegative value or atom, and then we're going to put the rest around it. So if I put sulfur, I have this, okay, and then I have a chlorine each, and chlorine has 7 valence electrons around it. And then I have oxygen. So if I see here, I would make bonds there, and then we have kind of a situation here. So we have 2 lone electrons on the oxygen, and then we have a lone pair here. So what happens is we're gonna make a bond here. And now sulfur can have more than 8 because it can break the octet rule. It's one of those that can. Oxygen cannot. If you remember, the octet rule can be broken by basically anything except for carbon, nitrogen, oxygen, fluorine. And then hydrogen will never have more than 2. So it's always 2, and that's it. It doesn't like more than 2 electrons on it. Okay, so we have that here. So that's usually what we draw, but here we have a bunch of different types of structures. And if we were to calculate the formal charge using our equation here, we could get, for this one, we would have 7 minus, there's 2, 4, 6, and then plus 1 bond. So that would be a 0. So each of these, or this one would be 0. So anything that looks like this, chlorine is going to be 0. So here we have a 0, a 0, a 0 here, 0, 0, 0, 0. Okay, and then for this chlorine, it's not the same because it has 2 bonds. So for this chlorine, we'd have 4. So we had 7 minus 4 plus the 2 bonds. So we have a charge of 1. So anything that looks like this chlorine where it's bonded, so this is 1 right here. Then we have this sulfur. Sulfur is 6 minus the 4 plus the 2, so we have a 0, so this is 0, this is 0, and yeah. So what I could do is I could go around and I can calculate for each and every single one, and then I can see which one has the least formal charge. But I'm just going to do it on this one just so you can see. So this chlorine, we have 7 minus the 6 and then the 1 bond. So 6 plus 1, because this is the bond, is 0. So we have a charge of 0 for this chlorine. For the sulfur, sulfur has 6 valence electrons minus the 2 lone pair and then the 4 bonds. So that equals 0. And then this chlorine is the same as this one, so that would be a 0. So we have a 0 here. And then this oxygen, so oxygen up there starts off with 6 valence electrons. It has 4 lone pair electrons and then 2 bonds. So that's a 0. So if you see, all of these are 0, the formal charges on these atoms, and that's why that makes this the most likely structure, because we have 0 for all the Lewis structure, or for all the formal charges of these atoms. We want it to be closest to 0. Whereas if we did the calculations on any of these, that would not be the case. We would find that some would be -1. So if we look here at this chlorine, it's 7 minus the 6, but 2 bonds. So that's already -1. So because we have a formal charge on that chlorine as -1, we can already tell that this is much more stable because all of them are 0. So remember, with formal charges, you calculate literally for each atom using this formula, and then you see which structure, Lewis structure, has the lowest or closest to 0 formal charges for its atoms. Okay. So now let's talk about resonance. So formal charge and resonance don't necessarily relate. Formal charge is just telling us what the charge is on that atom using that formula. Resonance talks about if you have a Lewis structure or compound, can there be more than one place to put a double or triple bond? That's basically all it's saying. So if I were to draw nitrogen dioxide, again, this is a weird one because we have 5 valence electrons for nitrogen and then 6 for each oxygen. So we end up with 17. So we end up with a weird one electron on the nitrogen. So this is the structure of a nitrogen dioxide. Again, very strange because we have 1 electron here. And what happens is this, we have 2, 4, 6, 8, 10, 12, 14, 16, 17. We have this double bond here. But I can write this structure also like this. So instead of putting it on that side, I could put the double bond on the other side, and it can go with the other oxygen. And what this is saying is it goes back and forth. So it's not this way or this way, it's going back and forth and back and forth and back and forth. And that's what resonance is. It's this double bond going back and forth between the 2 possible oxygens. Same thing with ozone. So with ozone, we have 1, 2, 3, 4, 5, 6. So what ends up happening with ozone is we have bonds here, bonds here. This one is unhappy. So instead of us violating the octet rule, because we cannot do that, this is what will happen. One of these will go over here to this oxygen, and then this other one, to fulfill the octet, will create a double bond. So we'll end up with this. And you can see all of them have 8 around each other. That's great. But it doesn't mean that this double bond is only on this oxygen. It can go like this. And then now we have 2 possible ways to draw this. And you can see it goes back and forth and back and forth. The double bond moves from each oxygen. Okay? And that's literally what it's saying. That's what resonance is when you have a double or triple bond and it can go back and forth between different atoms because they're the same atom. They have the same number of bonds possible and the same number of electrons possible. So now, the rest of these don't have anything. We have Cl4, and chlorine around. So there's no resonance to be had there because they're all single bonds. Water is this. There's no double bonds, so there's no real movement of anything. So that's why these two are considered resonance structures. Hopefully that helped you with resonance structures. So remember, formal charge and resonance structures are not necessarily tied together. You can use formal charge to see where the double bond actually go. If you had, like, let's say NO2Cl or NOCl or something like that, and you had to have a double bond here, then you can talk about possibly like if does a double bond go on the oxygen or chlorine, then you can use formal charge to calculate and make the correct structure, but not necessarily just, you know, they're not associated with each other. Formal charge is just, the only thing we're doing is finding the charge on each atom and then seeing what the correct structure is. That's it. Okay? So now some of you guys asked me to review, just want to make sure I went over everything. Actually, I had this question here. It said, not sure how to ask the question, but when you're given bond lengths, you get answers to choices like this and so on, how do you figure that out? So the way you figure it out is, let's say we have this. Right, and then we have a OH here, something like that. So we have something like this. And let's say that we want to talk about the bonds. So we want to see, like, okay, this is X, this is Y, this is Z. So whenever you have resonance, and in this case, we can have resonance between these 2 oxygens. They can, because this double bond can be here, or it can be there. It moves back and forth. Okay? So if we have this, then that means that because these go back and forth, we can have some, we're going to have the same bond length. And with resonance structures, if you remember anything about the bonds, is single bonds are going to be the longest. So single bonds are the longest. Then we go to double bonds. Those will be shorter than single bonds. Then we go to triple bonds, which would be the shortest. See if I can. Those will be the shortest, okay? So then this one's resonance, these bonds where it can go back and forth, they're in between. So if we have this is a single bond. We don't have any resonance here, so this is going to be the longest bond. The reason, if you just look at it like this and you're like, oh, well, this double bond is shorter than this single bond, so I would say X is equal to Z, and then both of those are greater than Y. But that's not what's happening here. We have resonance between these two oxygens, so it's going to go back and forth. So in reality, Z and Y are the same. And then X is going to be longer than both. So X is going to be longer than both of these. And that would be how you would answer that question. So you really need to look at the structure. First, you need to see, do you have resonance anywhere? And remember, if you have a double bond, that kind of gets your attention. If you have a double bond and it could possibly go on the same, another element that's the same, so it could go, and you're like, I wonder if it can go here, and then you draw that structure and you're like, oh yeah, it kind of makes sense. Then you have resonance, so those are going to be the same length, okay? If you don't have resonance, then we follow this. The single bond is always the longest, the double bond's a medium, and then shorter. If we do have resonance, for like here, it's going to go in between. So resonance are going to be like that, and then go in between. So let me make this a little bit more clear. So our first and our longest is going to be our single bond. It's going to be like that. Then in between, we have our resonance double bonds. And resonance means that we can go back and forth between two. So we'd have this. Then we have double bonds. And then we have our resonant triple bond. So we can go triple bond between two. Okay. And then the last, the shortest would be our triple bond. So that the length decreases. So the bond length decreases the more bonds you have between those atoms. And I hope that can help you. Hope that kind of explains it. Okay, and then the last thing we wanted to go over was this molecular geometry. Now the truth is, you're probably not going to be taught or asked to memorize this or be like, oh, okay, if we have BF whatever. I gave you some just so you can look and familiarize yourself with this. Really what you're going to want to know are like the bond angles. If we had something like this, are the bond angles all going to be the same? And if you look here, they're not. So if we look at our T shape, we have a 90 here, we have so yeah, we probably have 90 right there. But if you look at something like this, like the seesaw, the sawhorse or the seesaw, you're going to have different bond lengths. So it's just making sure that you understand that. That's it. Okay. So if you can kind of like review these right here and see what happens, the shapes. Remember the lone pairs are on the central atom. So here we have, we're going to do for BF3, we have 1, 2, 3, 4, 5 bonding areas or bond, electron domains. So we have 5 electron domains. And then we have 2 lone pairs, because we have this one and then we have this one. So 2 lone pairs and the 5 bonding domains would be T-shaped. Okay? And that's how you would do it. Like for oxygen, water, we have 4 electron domains, so 1, 2, 3, 4. And then we have 2 lone pairs, and that's why it is bent. So it's just really looking at this, and during the test, I'll have this available on the screen for those that need it, or you can, look at this or get one and put it into your notebook. Okay, so I hope I answered your questions. If you have any more, just make sure to email me, and then I'll go ahead and answer them. Okay, have a good day.